Alright, so let's see what happens if we want to analytically, by hand determine what's happening at a vertical asymptote. So again, this is the same equation as before, and in the previous example we listed that there was a hole at -3 and an asymptote at 1. So notice how we are now approaching that asymptote, but on different sides. So we know that if a rational function has a non-removable infinite discontinuity, that's a fancy phrase meaning vertical asymptote. And since the y values do not approach one specific value from both sides of a vertical asymptote, then we know the limit does not exist. That's our basic definition of a limit, how we must be meeting at the same point. If we don't, either a jump or an asymptote, the limit does not exist. So we can determine, though, what's happening on either side of the asymptote. So we're going to be looking at one-sided limits. Now, if you think about an asymptote, the only options that you have is a graph is either going to go up on one side or down on one side. So our only resulting options would be infinity or negative infinity. And that's what we're going to try to figure out here. So we already know that there is a vertical asymptote at 1 after we did that canceling process. We're going to determine what's happening on the left-hand side of that vertical asymptote. Do we happen to go up or do we happen to go down? Now this is where we're just going to be a little strategic. We want to pick a point to the left of 1. So for instance, 0.9. And if we were to substitute in 0.9, we want to see if our result would be positive or negative. So 0.9 plus 1 is a positive value. 0.9 minus 1 would be a negative value. Positive divided by negative means negative. So on the left-hand side of this asymptote, as we approach 1 from the left, the function is going down forever on that asymptote side. Let's go ahead and check the right-hand side. So again, we know there is an asymptote at 1, but we're going to check to see what's happening on the right. Do we go up or do we go down? So if we plug in, substitute in 1.1, 1.1 plus 1 is positive, 1.1 minus 1 is still positive, positive divided by positive is a positive result. So on the right-hand side of this vertical asymptote, the graph actually goes up. So after we can determine where a vertical asymptote is located, we can test either side of that location, in this case 1, and see whether we go down or up on either case. Alright, so those are holes and some vertical asymptotes. Another method that we can use to help us evaluate limits by hand is what's called rationalization. And you may or may not have heard of this word before, but rationalization is a process or a technique that we can use whenever our function involves a square root somehow. And in order to do that, we're going to use what's called a conjugate. So we'll talk about that in a second. So the graph of g of x is pictured to the right, and often rationalization can be used to evaluate a limit by hand. So notice how if we were to try direct substitution, remember that should always be our first try just to see if it works. If we plug in 3, we'll have the square root of 4, which is 2. 2 minus 2 is 0. If we plug in 3 down below, we'll get 0 again. So there's that indeterminate form. So this is telling us the limit might exist. We just have to work a little bit further to see if it actually does. This is also signifying that we most likely have a hole in the graph. And if you look at the picture or graph that we have here, we clearly do. So we're going to see what else we can do with this by hand to evaluate the limit. Now, just as a little heads up, since we do have a graph, we could guess what this limit answer should be. If we were to approach from the left and the right, clearly the limit exists, and that height of the hole maybe is a quarter, somewhere in there. So let's see if we can get something close to that estimation while we do this by hand. Right? So we're going to utilize what's called a conjugate. Now, a conjugate sounds very difficult, but it's actually an easy concept. A conjugate is where you take the square root portion of your fraction, and we're going to keep the terms the same, so the same square root and the same number, but instead of subtraction, we're going to change it to addition. Okay, so we're keeping the terms, but we're just changing the operation between them. What we're going to do is take this conjugate and multiply it on top and down below. What we do to one side of a fraction, we have to do to the other. Now we're going to multiply these two fractions together, but we are only going to multiply the top part because that's where the original square root was. Okay, so I want you to take a look at this. The square root of x plus 1 times the square root of x plus 1, the square roots would cancel each other out, and we're left with x plus 1. Now, if we think about the FOIL process and what's going to come next, we would have the square root of x plus 1 times 2, and then we would have the square root of x plus 1 times negative 2. Notice how those terms would eventually cancel out because one's positive and one's negative. So you may not have to write those. Okay, that's what's nice about this conjugate. Since we kept the terms the same and we switched the sign, those middle terms of the FOIL process, okay, that O and that I, will cancel each other out because one's positive and one's negative. So when you're using a conjugate, you really only have to multiply the first terms and the last terms together. So we already multiplied the first together. Let's go ahead and multiply the lasts. Negative 2 times positive 2 would be a negative 4. The bottom two are going to give us a headache if we actually go through that FOIL process. So we're going to strategically keep them as their separate factors. Okay, now notice what's going to happen. This x plus 1 minus 4, that's going to change to an x minus 3 after we combine those like terms. And since we have an x minus 3 down below, those would cancel each other out. Okay, if something cancels, it's resembling a whole, which we said was already there. So it's starting to take shape. We're going to have a placeholder of 1 up top since everything went away. And we're left with the square root of x plus 1 plus 2 down below. Okay, so even though the substitution of 3 did not work initially, because we got 0 over 0, we are now going to try substitution again to see if it'll work this time. So the original way the equation looked didn't quite work for us, so we simplified it using a conjugate, and let's see if this simplification is any better for us. So let's go ahead and substitute in 3. 3 plus 1 is 4, square root of 4 is 2, 2 plus 2 is a fourth. And notice how that confirms what we thought the limit was. As we approach from the left and the right, we get closer to that hole, which seemed to have a height of a fourth.